Welcome to my YouTube channel. So today I'm going to deliver a section on Gauss law and its applications. So in electromagnetic fields, this is one of the very important law used to determine the electric flux density in different conditions. So Gauss law constitute one of the fundamental electromagnetism. So it is very important law of electromagnetism. So it states that total electric current passing any closed surface. So if you take any closed surface, so total electric flux passing through this closed surface is equal to the total charge enclosed by that surface. So total charge, suppose your charge Q is enclosed on the surface means, so this law states that so electric flux psi is equal to the total charge enclosed by that surface. So total electric flux passing through any closed surface is equal to total charge enclosed by that surface. So psi is equal to Q. So this is called Gauss law. So other expressions are also available. So we are going to derive. So psi is equal to Q enclosed. That is the charge enclosed on the surface. So that is equal to psi is equal to surface integral of d psi. So if you integrate a small range of electric flux, so we are getting the overall flux, that is psi is equal to surface integral of d psi. So this can be written as surface integral of d dot ds. So d is called electric flux density. So electric flux is equal to surface integral of d dot ds. So electric flux density. So we are going to calculate electric flux density using the Gauss law for different applications. So Q is called total charge enclosed. So that is equal to volume integral of ρV into dV. This is ρV is called volume charge density. So based on the above expressions, so we are going to write Gauss law as Q is equal to charge Q is equal to surface integral of d dot ds. So surface integral d dot ds that is equal to volume integral ρV into dV. So volume integral ρV into dV. So Q is equal to surface integral d dot ds that is equal to ρV volume integral ρV dV. So based on the concept, ρV volume charge density is equal to divergence of electric flux density. So ρV is equal to del dot D. So we are going to write Q is equal to surface integral d dot ds that is equal to volume integral del dot D into dV. So these are the different formation of Gauss law. So psi is equal to Q. So Q is equal to surface integral d dot ds or Q equal to volume integral ρV dV. So this is the Gauss law. So next, with the help of Gauss law, so I'm going to find out the electric flux density at point charge that is on the surface of the point charge. So let us assume, so this is the point charge that is sphere in shape. So Q is the charge, so it is on the center of the origin, that is origin of the sphere. So point charge is located at the origin. So with the distance r from the Q point charge, so we are going to consider the point P. So at a distance r from the point charge Q, so point is P. So in that point, so we are going to calculate the electric flux density D. So before applying the Gauss law, so this should satisfy the symmetric conditions. So surface, spherical surface containing the P will satisfy the symmetric conditions. So origin will be center. So the surface is called Gaussian surface. So Gauss law will be applicable for the only Gaussian surface. So this is the Gaussian surface. So D is everywhere normal to the Gaussian surface. So according to this, so we are going to write So by applying the Gauss law for the point charge, so we are getting the formula. Gauss law is equal to Q is equal to surface integral d dot ds. So here we mentioned so d is equal to dr into ar. So we are applying the magnitude value dr into surface integral ds. So surface integral ds for the spherical system. So this is a sphere in shape. We are going to apply the formula. Surface integral ds is equal to integration limit pi is equal to 0 to 2 pi, theta is equal to 0 to pi. So for spherical surface, ds value is equal to r square sin theta d theta d. So if you evaluate this equation, so finally we get the formula 4 pi r square. That is surface area of the Gaussian surface. So we are going to write this equation. So instead of surface integral ds is equal to 4 pi r square. So our equation becomes q is equal to dr into 4 pi r square. So we are simply writing dr as d. So d is equal to q divided by 4 pi r square. So this is the magnitude value. So into ar, this is the unit vector. So difference electric flux density due to the point charge. So d is equal to q divided by 4 pi r square into ar unit vector. So q is the origin. So at a distance r from the point charge, we are going to determine the electric flux density d. That is equal to q divided by 4 pi r square into ar. So next we are moving for the another applications to determine the electric flux density. So due to the infinite line charge. So this is the circuit diagram of the infinite line charge. So we are taking the cylindrical gas in surface. So line charge is equal to rho L coulomb per centimeter. So deposited on the cylindrical surface. So this is called the Gaussian surface. So rho is the radial distance. So between the center of the axis to surface of the cylinder. So we are mentioning the point P on the surface. So now we are going to calculate the electric flux density at the point P due to the line charge rho L coulomb per meter. So this also satisfies the symmetry conditions. So rho L uniform charge is distributed along the z axis. So in this case, d is equal to, because it's a cylindrical coordinate system. So d is equal to d rho into a rho. So d rho into a rho. So rho L into L is equal to Q. So this is the Gauss law. Rho L into Q is equal to Q. That's equal to surface integral d dot ds. So we are going to write d as a d rho into surface integral ds. So surface integral dl is equal to 2 pi rho L for the Gaussian surface. This is the cylindrical shape. So surface integral ds is equal to 2 pi into rho L. So we are getting the formula. So PL into L is equal to d rho into 2 pi rho L. So from this equation, we need to calculate d, that is a dp. So d is equal to rho L into L divided by 2 pi rho L. So L will be cancelled. So finally answer d is equal to rho L divided by 2 pi rho into a rho. So this is the flux density due to infinite line charge. So we are determining the electric flux density value with the help of Gauss law. So next application is electric flux density at a point P due to infinite state of charge. So this is called the infinite state of charge. So in that, rho s coulomb per meter square charge is distributed evenly. So rho s is the charge distribution, surface charge density coulomb per meter square distributed on the infinite sheet. So we are going to take small portions from infinite sheet. So this is the small portion. So in that, so this is the top of the surface. This is the bottom of the surface. So that is called Gaussian surface. So we are going to calculate electric flux density at the point P. So this is cross section area. So here point P. So plus D is available, negative D will be available. So D to D infinite sheet of charge rho S. We are going to calculate electric flux density at point P. So according to the Gauss law, so rho S into surface integral ds is equal to q. So that's equal to surface integral d dot ds. So there are two surface, top surface and then bottom surface. So we are taking dz as the electric flux density. So d is equal to dz into az. So dz into integral top into ds plus integral bottom into ds. So integral top into ds is equal to, this is the cross sectional area capital A. So this is the cross sectional area capital A. So integral bottom into ds also, so cross sectional area A equal to cross sectional area. So here also integral surface integral ds is equal to A. So rho s into A is equal to, so dz into A plus A. So I'm going to simplify this equation. So going to write this equation. So rho s A is equal to, so dz into 2A. So both side A and A will be cancelled. So we need to determine D. So D is equal to rho s by 2 into AS. So D is equal to rho s by 2 into AZ. The next one is capital E. The relationship between, so D and E is equal to so epsilon E. Or E is equal to D by epsilon. So using this formula, we are easily calculate the electric field intensity. E equal to, so D divided by epsilon naught. That's equal to D value is equal to rho s by 2. So rho s by 2 epsilon naught into A is that. So this is the final answer. That is electric field intensity due to the point P in infinite sheet of charge. So I'm going to conclude the session with small recap. So Gauss law means total electric flux passing through any closed surface is equal to the total charge enclosed by the surface. That is psi is equal to q enclosed. So that's equal to q. That's equal to surface integral d dot ds. That's equal to volume integral rho v dv. So this is the Gauss law. So with the help of the Gauss law, we are able to calculate the electric flux density at different conditions for the different Gaussian surface. So we are going to take point charge. So it is a Gaussian surface, rho by c are satisfying the symmetric conditions. So here d equal to dr into ar. So q is equal to, according to the Gauss law, q is equal to os d dot s. That's equal to dr into surface integral ds. So surface integral ds covers here is equal to 4 pi r square. So d is equal to q divided by 4 pi r square into ar. This is the electric flux density due to the point charge. The next one is infinite line charge. Here rho L charge is uniformly distributed on the cylindrical Gaussian surface. So assuming the point P and the surface, the radial distance, so calculate the electric flux density at that point. So rho L into L is equal to q. That's equal to surface integral d dot ds. So that's equal to d rho into surface integral ds. So that's equal to d rho into 2 pi rho L. For cylindrical coordinate system, integral ds is equal to 2 pi rho L with a charge density rho and L means. So from this equation, finally, d is equal to rho L by 2 pi rho into a rho. So Third application is infinite sheet of current. So this is infinite sheet of current in that the OS charge is distributed uniformly. So this is the area. So this is the top surface, the bottom surface. So we are going to calculate the electric flux density at a point P. So that's equal to OS into surface integral ds is equal to Q. That's equal to OS d dot ds. That's equal to dz into so top ds plus bottom ds. So it becomes OS into A. So integral d dot ds is equal to A. OS into A. So d is that into this part goes what equal to cross section area A. Here also bottom is equal to cross section area A. So this equation becomes 2A into dz. So simplifying this equation, trying to get the flux density OS by 2 into AZ. So next, so from this relationship between G, D and E, so E is equal to D by epsilon naught. So electric flux density OS by 2 epsilon naught into AZ. So this is very important. So law in electromagnetism used to determine the electric flux density and the electric field intensity for the differential Gaussian surface. Thank you.